In this video, we begin our discussion on continuous probability distributions. So, to get started, we want to ask ourselves the major question: when does a continuous random variable have a normal probability distribution? You want to remember that a continuous random variable usually arises from a measuring operation, as opposed to a discrete random variable whose values are obtained after a counting operation. You see, when we measure quantities such as IQ scores or the birth weights of babies, they usually have a distribution that tends to be symmetric and bell-shaped. That distribution, usually called symmetric and bell-shaped, it has an all-encapsulating name known as the normal probability distribution. Let's consider the histograms of IQ scores for 10 randomly selected adults given here in this picture. You will note that as the class width decreases for each of the bars in the histogram becomes closely approximated by a smooth curve. That smooth red curve is known as the normal probability distribution curve. So we can say that the IQ scores of this 10,000 randomly selected adults follows the normal probability distribution. More to come on that, just to illustrate the reality of this distribution. So, in general, we say that a continuous random variable, such as the IQ scores, is normally distributed or has a normal probability distribution if you draw the relative frequency histogram and it has the shape of the normal curve. Take note that for the normal curve, there's a point where it starts to slope downward faster than at any other point on the graph. This is called the points of inflection, and usually it is the point where it usually corresponds to where you have the mean minus the standard deviation and the mean plus the standard deviation. A little more detail on this, just to bring it to life. Let's consider an example where X is a random variable that represents the heights of adult men in the United States. So on the x-axis, I'm going to keep heights there. And instead of writing heights, I can just write X as a placeholder. Now, we read further. Data collected in the past on the heights of adult men shows that the average height of adult men is about 70 inches. Sketch the frequency distribution of the height of adult men in the United States about the mean height of 70 inches. Comment on the shape of the distribution and an appropriate model for the distribution of data. Well, let me pick a point here to record the average height of adult men, which is 70 inches. So here, we're talking about heights measured in inches. I am going to let on the y-axis or the vertical axis be the count of men who have the different heights, This in statistics will be called frequency. You can use your frequency or your relative frequency. And this will represent in the general population of adult men in the United States, how often do we see those whose height is 70 inches? Well, if that is the average height, let me draw a line that goes this much. Well, how high up this line goes is an indicator of how often I see this height of 70 inches in the general population of adult men. Now I'm going to think further. If I pick the height of basketballers, so let's say about 80, 90 inches, thereabout, whatever have you, and I draw the line this much, you agree with me that I've done something wrong. We don't see many more basketball height men in the population than average heights. So this wouldn't be an appropriate representation. In fact, there should not be as many as those who have average height. So can be said for those who are challenged height-wise. And so, in this case, we don't have as much too. Now let me decide to connect these pieces here. So I have this. So this looks like a floating ghost. This, of course, is the normal curve. You see, all of the stories I've told so far about this height, simply, I could speak to another statistician in another part of the world and just say, hey, the height of adult men in the United States has the normal probability distribution. And that will immediately capture the fact that there is a particular height that is more often seen in the population, and that there are other heights that are above that height and below that average height, but that the distribution, or how often you see those heights that are above the average and that are below the average, are evenly spread to both sides of the average height. Whenever we see a phenomenon like this in statistics, we simply summarize the whole story by saying that the heights of adult men has a normal probability distribution. So this graph that we've just drawn of a continuous random variable, which is the height of adult men, is called a normal probability curve, or simply a normal curve. In mathematics, a model is an equation, a table, or graph used to describe reality. An example of this model is the normal curve. So we can say in this instance that the normal curve models the heights of adult men in the United States. In general, a continuous random variable is normally distributed or has a normal probability distribution if, when you draw the histogram, it has the shape of a normal curve. Now, there's a part of this curve we have not talked about so far, and that is this area under the curve. What does it represent? When you draw the normal probability distribution curve, the area under this curve, which I'm tracing out in blue, is representing this area is representing probability. So probability is represented by area under the curve. The sum of all probabilities is always equal to 1. So the sum of the total area here, it always adds up to 1. Now, we begin to probe a little bit deeper into the characteristics of the normal curve. And to begin, we want to look at the parameters of the normal distribution curve. The parameters are the descriptive values of the normal distribution curve. And there are two of them. The mean, that will be the number that represents what is most often seen in the general population, and then the standard deviation, which represents the spread of values away from the central value. So, to illustrate, the mean in this case, in the red one, is 0, which is the central value, and the mean for the blue normal curve is 3. Then, in this case, they both have the same standard deviation, which is a measure of how other values are spread away from what is typically observed in the observation. Now, to illustrate, so note that the normal curve with the mean of 3 is further along to the right than the mean, which is equal to 0. And that will be an indicator of the relative locations of 0 and 3 on the horizontal axis. Then, what is the job of the standard deviation? The standard deviation is a measure of spread. If I trace out the red or purple curve here, this shows that most of the points are bound together in around a particular location on the horizontal axis. And this indicates that the standard deviation is definitely small or smaller than the standard deviation of the normal curve, which is blue. So this tells us that this guy, the normal curve, has a larger standard deviation since it is more spread out. So the larger the standard deviation, the more spread out your normal curve is. To understand or help us better understand the concept of what we're talking about, let us consider this example. So in this example, we're told that one graph in the figure to the right represents a normal distribution with mean of 15 and a standard deviation of 2. And there is no doubt about that would be the blue one in this case. And the other graph represents a normal distribution with a mean of 7 and the standard deviation of 2. Determine which graph is which and how you know. Well, I know because the mean represents the central value, what is very much more observed in the population, and that bump here is an indicator that 15 is the most often observed value in this population over repeated samples. Whereas in this case, 7 is the most repeated value here. Or most observed value here. So it stands to reason that the standard deviation, the normal curve B is the one that has a mean of 15 and standard deviation of 2. And the other one, the normal curve, is A, which has a mean of 7 and a standard deviation of 2. With that said, we proceed to a rule that is closely tied to the normal distribution curve, because this rule only applies to distributions that have the normal probability distribution. So if X is a random variable and it has a normal distribution of mean, that is the number in the middle, and a standard deviation, which indicates how numbers are spreading away from what is typical, then the empirical rule says the following. The 68% is saying that if you collect data on the mean height of men and the average height is 70 with a standard deviation of, let's say, 4. So if the standard deviation is 4, it means that 70, if you take a step from 70, a step in English or in statistics, we say a standard deviation. So one standard deviation will be 1/4, one step of length 4 from 70. And that takes us to 74 forward. And if you take a step backward, that will be one step of 4 backward, and that will be 70 minus 4, which is 66. That will take you to one standard deviation below and above the standard deviation. So I'm going to shade this. What percentage of adult heights will be in this range from within one step or one standard deviation measured either above or below the mean? It is 68%, same as 0.68. Now the story continues rather. What about 95? Well, we are saying this time, if this is the mean, rather, we always locate the mean first. Take a standard deviation, the first standard deviation of sigma equals 4. That takes you to 74. Take another standard deviation of 4. That takes you to 78. And then 2 steps backward, that will also be 70 minus 4, 66. 66 minus 4, 62. How much of the heights, or what percentage of the heights of male lie within two standard deviations from the mean? So either forward or backward. The number from the empirical rule is 95%. So you have 95% or 0.95. Then for 3 standard deviations, let us see. For 3 standard deviations, that will be from 70, 74, 78, plus another 4, that is 82. 70 minus 4 is 66. 66 minus 4 is 62. 62 minus 4 is 58. So in this space, what we are saying is if you capture often, how many heights lie within that range? It is about 99.7%, same as 0.997 proportion-wise. So this is a summary of what the empirical rule is saying. This rule was used back in the day for approximations when there were no calculators. So we can capture these three pieces and take it to the next page. And we're going to summarize all of that here. So first of all, we saw earlier that within one standard deviation, we have 68%. The normal probability curve is symmetric about the mean, which means that is the point where it divides the distribution into approximately 2 equal halves. So if from here to here is 68%, let us see. If this is 68%, so it means 0.34, 34% here, 34% to the right. Then this is 68%. We learned earlier too that within two standard deviations, you have 95%. Well, 68% is already here. So we are left with what is left for these pieces to share. 95% minus 68%, that will give 27%. 27% divided by 2, that will be 13.5%, 13.5%. Same as 0.135, 0.135. So now we proceed. For 3 standard deviations, we want 99.7%. So it stands to reason. Before we continue, let us shade the one for 2 standard deviations. Then let's grab another color for 3 standard deviations. So we want to know how much should be in this new color. So that will be 99.7 minus 95%. That will be 4.7%. 4.7 divided by these two, that will be 2.35%. 2.35%, which is same as 0.0235. Then we have the last tiny bits here. It is this tiny bit here, and then this tiny bit here. So with that said, let's see. What would that look like? This tiny bit and this tiny bit. That will be 100%. 100 minus 99.7. That gives 0.3%. So this would go to, let's see. So we have 100% as it stands minus this value is 0.3%. Shared, that will be 0.15% and 0.15%. How can this be used? Let us see the next example. In this example, we are told that suppose the heights of adult males have an average or mean of 70 inches and a standard deviation of 4 inches. We're going to let X represent the heights of adult males. Using the empirical rule, we want to find the following approximate probabilities. So the normal distribution has been summarized here. And so we want to look at the different spread in this case. So we have the probability that X is greater than 70. Remember, this is 70, 74, 78, and 82. This is 66, 62, and 58. So for the first part of the question, we want the region probability of X greater than 70. That would be shading this part. So since the whole probability is 1, we're already shading half of it. So that gives us 0.50. So as it stands, we have that answer done. Then the next question, probability of X greater than or equal to 70. Take note that our x in this case is a continuous random variable, not discrete anymore. If it is continuous, then greater than 70 is exactly the same thing as greater than or equal to 70 because you're not counting discrete values anymore. You're not counting as 70, 71, no. You're counting as decimal or continuous values. The first decimal number after 70, what is it? Are you going to say 70.1? What about 70.001? Well, as it stands, you observe that decimal numbers are so smooshed, so closely together, that greater than 70 also passes for greater than or equal to 70. So these have exactly the same answer because they represent the same region. All right, then with that said, we proceed to look at probability of x less than 70 or less than or equal to 70. Of course, this should both be equal. So as it stands, we're looking at this region. So this will be equal to 0.50. Then for question D, we want to look at the probability between 62 and 82. So that will be 62 and 82. Okay, so looking at that, that will be 13.5% plus 34% plus 34% plus 13.5%, then plus 2.35%. That will be 95%, two standard deviations, plus the extra 92 plus the extra 2.35%. That will give 97.35% or 0.9735. Then what about probability of between 62 and 78? Between 62 and 78, 62 and 78, so we have 74 here. Let's see, 62 and 78. You agree with me, that is exactly two standard deviations from the mean. So according to the empirical rule, that needs no calculation. It is 95% or 0.95. Then, again, we look at the last one here, which is probability between 62 and 74. 62 and 74, right there. So this will be equal to 68, 13.5 plus 68. So let's see. That would give 81.5%, which is same as 0.815. This is that probability there. Then we continue to the last question on the empirical rule, in this case. From 1984 to 1985, the mean height of a 15 to 18-year-old male from Chile was 172.36. So that will be the number in the middle. The mean goes in the middle. And the standard deviation, sigma, was 6.34. So if I take a step forward, that step measures 6.34. And so this would be, this number, the standard deviation ahead of the mean, will be 172.36 plus 6.34, which is 178.7. So if I took another standard deviation from 178.7, that will take me to 185.04. So let me register that, 185.04. Then plus another 6.34, that takes you to 191.38. Going backwards, 172.36 minus 6.34, that takes you to 166.02, minus another 6.34, that'll be 159.68, minus 6.34, that takes you to 153.34. Okay, so with that said, we want to use the empirical rule to answer the following questions. Question A. About 68% of the heights lie between what two values? Well, going back to the empirical rule, we expect 68% to lie within one standard deviation of the mean. So from the mean, this is the region that captures one standard deviation of the mean, which according to the empirical rule should have 68%, and it lies between these two values. So our answer here is between 166.02 centimeters and 178.70 centimeters. Question B. What percentage of the heights are greater than 159.68? So let me erase this, and we are interested in one percentage greater than this value. So take note that earlier, if we compare this to what we had earlier, here, that would cover the region we're interested in that we've just shaded for this question, would cover from 2 standard deviations below all the way above. So from 2 standard deviations below and all the way above. So that would be 0.135, 0.68, 0.34, 0.34, 0.135, 0.23, 0.0235, and 0.0015. So this would be, looking back, let's key in those values there. So here I have keyed in all the values. This would mean I will need to add up 1, 2, 3, 4, 5, 6, all of these numbers. An alternative way will be to add up all of this. That is, let us see. Another way would be to add up the colored red ones. So I would say 100% minus 0.15% minus 2.35%. And that would give me 97.5%, same as 0.975. That clears up that answer. Then the next part of the question is, what percentage of the heights are greater than 198.38? So that would be this region, which from the picture is merely 0.15%, same as 0.15 divided by 100, which is 0.0015. Then finally, what percentage of the heights are between 159.68 and 178.7? So between 159.68 and 178.7, that will be 13.5% plus 34% plus 34%, and that will give 81.5%, same as 0.815.